All right, so let's carry on our discussion in chapter 2. We reached the point that we understood how we're going to distinguish different instructions and how many, and we saw many other types of instructions in RISC-V, right? We are up to the point that we want to present something like procedure. So procedure or function, I'm sure most of you have already used a function in your in object programming languages. So we call it either a procedure or function, and it's a one neat tool to reuse the code that you want to use many times. So perhaps you write a function called print, and then you want to call that print like 200 times in your code. So every time you don't have to write it from scratch, you just call the function or a procedure here. So let's see how we're going to define a procedure in RISC-V using our ISA that you already know. So there are some simple steps for that. So the first step is we want to make sure when we start a procedure, we won't lose of the returning address, right? So when a procedure starts, we want to make sure that we place all the parameters in dedicated registers, which are in RISC-V from x10 up to x17, right? So after that, after we make sure we won't lose any register's value to come back, we're going to transfer control to the procedure, right? After that, we're going to acquire storage from the memory for that procedure, and then we do the operations of the procedure, and then we place the result in register for the caller. So in every procedure, you have a caller that calls for the procedure, and another one which is a callee that do the exact opposite job, so returns back to the caller. So at the end, we want to make sure that we return to the place of the call at the first place. Otherwise, we are lost in our execution. Okay? So because of doing a procedure, let's get to know some other operations here. So JAL and JALR, so jump and link register are these procedure ISAs that we're going to use in RISC-V. So the first one, jump and link, is actually jump to the procedure label that we annotated with the name of the procedure. So if it was my print, so you're going to write it like JL X1 and my print. We're going to see an example in the exercise. So what it does is it address, it's going to put the address in X1, the register X1, and later when we make sure we have the address, because we want to return to that address after the procedure, it's going to jump to the target address, right? At the end of the procedure, we want to make sure that we come back to the first place. So we're going to use JALR, and what it does is just like JAL, it's going to jump to 0 plus the address of that X1. Okay? We can use these two for many variety of for loops or switch cases. So we're going to have some examples later on. So as an example, so we have a C code here. So my function or my procedure is called leaf example, leaf underscore example. So it's going to return a long int, okay? And it's going to get some arguments that are long in G, H, I, and J, right? So in the body of this procedure, I'm going to do the following. I'm just going to define F, right, as a long int, and then the F would be the result of G plus H minus I plus J. So pretty simple one, right? So now, before starting my procedure, now I need to make sure that I'm saving those returns on my stack. So those registers that I can use are X5, X6, and X20. So if you translate this code in RISC-V, you're going to see the following. So that's my leaf example. That's the procedure I'm doing. I'm starting line by line to make sure you get the idea here. So all right. So at first, one thing to consider is this SP is a stack pointer. So a stack pointer is always point to the last. Well, let me just show it here. It always points to the last address, and we are addressing it in bytes. The stack works this way, that it starts from high address and goes towards lower addresses, right? So when you add something into the stack, an operation that we call push, it's going to bring down. So after 3 pushes, you're going to have the stack pointer here. It's going to go from the high address to the low address. The reverse operation for push is called pop. So when you pop back those 3, the stack pointer goes back up in the high addresses. So the stack, it works as last come first serve, right? So this one was the first come, which is going to be last served. The last one will be served first, right? So it's a LIFO instruction. So I'll talk about it more later. So but for now, since we know that we have to, yeah.
Professor, can I use, instead of JALR at the end, can I use JAL over there?
Where?
At the end there is JALR X naught, like 0 X naught. Can I use
at the end?
JAL? Yeah.
At the end, no, because you're returning to the caller. You're the callina. At first you could use that, but at the end you're not. You'll figure out why. Okay, so now I need to save my X5, X6, and X20 on stack, right? As an example, these three you see here. So since I'm addressing my stacks 8 by 8, so I need to change that position of my stack pointer by 3 8s, right? So by pushing these 3, I'll have to make sure that, and since I'm starting from a high address towards a low, so I have to deduct 3 8s from my address, from my stack pointer, right? So I add that minus 24, so my stack pointer will be stack pointer minus 24, so it's going to go down into the stack to a lower address. I'll start saving those X5, X6, and X20. So that's why you have SDX5 16, SDX6 8, and SDX20 0, right? We push values onto the stack by creating space for 3 double word. That means 24 bytes, right? Using addi. And then we store them. Okay, so now we reached up to the point that we want to actually execute the procedure. So we wanted to have an add here for these two. The result will be stored at X5. There was another add, I plus J. The result will be stored at X6. So these are pretty straightforward. The final F would be the deduction of X6 out of X5, which will be stored at X20, right? And now, I need to do another addi to copy F to return register. And then after I'm done with my execution of the stores, now I need to do the reverse thing, going back on the next slide. So when I'm done here, I need to pop them out of the stack one by one, and then this SP, which is stack pointer, goes back up to its original place. So here I'm going to store X5, X6, and X20 from the stack, right? And then I'm going to addi this time plus 24 to the stack. I'm done with my procedure, and then it's time to return to the caller. This procedure is it just runs once, right? Because you run it once. We call this sort of procedures leaf procedure. Just like a tree, when you reach a leaf, there's no other branches outside, right? So we call this type of procedures leaf procedures. We have another type of procedure called non-leaf that is going to be a little bit more complicated. We're going to see it in a few slides. Questions?
I got the answer.
Okay.
Sorry, when you're saying the -24, is that the address?
Yeah.
So how big is the address? Like when you say -24, is it from like -24 to 24, or like how big is that?
So it means whatever the address of a stack pointer was in a stack, just reduce 24 out of that. So 18, 28, 38. So this would be -24 up to here.
So it's from 0 to 24?
No, in a stack, this is your stack, right? The start is always the highest address. And when you go into the stack, up until it's full, we're going to go to up to lower address, right? Yep.
So that's why in JALR, what is the use of destination register in that?
That's 0?
Yeah, X0. Why we are
To return to the caller, right? I mean, in this case, you see here, X1, guys, this is a good question. So X1 contains the address of your caller. At the end of your leaf procedure, you want to make sure you want to return to that caller, right? So you were executing some part of the program here. You reach to this leaf example. So you want to make sure after you finish that, you won't lose where were you, right? You want to come back and then execute the rest of the code, right? So when you reach here, you are going to the address 0 of that X1, and it's going to return you to the caller. There was another, yeah.
So why don't we use like division instead of like adding? And for addi, why don't we do like the division first?
Which line?
The first line?
This one, -24?
Yeah, why don't we use like 3?
Oh, I see. In general, yeah, I mean, this could have been possible, but in general, since we are dealing with integers and it's binary, it's easier to implement that. Another side note to consider, always multiplication is more computationally intensive than addition. And worst of all is a division in computer. So anytime you had a chance to avoid division, just avoid it, right?
But I see like some examples like from a previous lecture. They're like using SLLI.
Oh yeah, that was a shifting, yeah.
Yeah, so why we don't use that? Like when should we know we have to use that one?
I mean, here, because you're going relative to the address of the first SP, right? You just know that you want to push 38 double words into your stack, right? That's all you know. The only way you can compensate the difference is by doing it by 24, which is 3/8. If you want to divide it, how would you divide it? Because you didn't know the first address at first, because it's relative, right? So here what you say is wherever you were as a SP, I don't care, just -24, right?
And also I have another question.
Yeah.
I don't know what is 0 and like inside the parentheses we have like x1. So what is 0 exactly?
So actually we should have had this one as well here. So like these numbers,
Yeah.
these are the address in memory when you want to look.
Just 0, like 0 and inside the parentheses is p.
Which line?
SD, like fourth line.
Here.
Yeah. So what does this 0 mean?
So always when you have some value before the parentheses in many of the operations, it is referring to the address of the memory. So like this is like the 16th address 16 in your SP. This is your address 8 in your SP, and this is your 0. Because here you are going 8, 8, and 8, right? You're going down. Questions? Yeah.
Why did you go
3 addresses below SP?
Because in a stack we start with higher addressing, you see? The start is higher address, and when we push into the stack, we're going to go lower in the stack. So think about a stack as something like a placeholder like this, that you when you want to access something, right? So let me just try to just do something here. I can. Okay. So suppose this is my stack, right? As a placeholder. So first I'm putting this cover on, right? And then second I'm putting my tablet on top of that, right? Now when I want to take my tablet, when I'm going to take the first item that I can see, right? Which one comes first? My tablet, which came last, right? The stack works at last come, first serve. So last come, first serve. Or they call it LIFO style. We have also FIFO, which goes as queue. The first come will be first serve, right? So since the stack has a last come, first serve, it starts with a higher address that shows the top of the stack. When you push stuff into that, you're going to go into the stack, right? It's just one convention that works in computer.
So why can't you start? Why can't you do it without deducting SP by 4?
So do you have any other suggestion than deduction?
Just keep it as it is.
Keep it as this?
Where is it before minus 24? What's the value of SP before?
SP, whatever the value was from the previous code.
Yeah, so
that was.
just build onto that.
Yeah. Because at the end of the, I'm just looking at my phone. It's not readable. So before starting your leaf procedure, you would have perhaps gone a long way with executing so many other code, right? After executing your leaf instruction, you want to come back to that same place and carry the rest of your code, because you were like running some code and then you were calling it leaf underscore procedure, right? And then the rest of the code, and then you might want to call it again. So at each time when you call it, you make sure that you won't lose the rest of the code you want to come back. So there should be a pointer to point that for you. We have other type of pointers that you're going to see here that works in different scopes. One scope for your leaf procedure is your stack pointer. Okay, it just helps you won't lose track of what have you been doing before that.
So RISC-V being little endian, shouldn't the low
Could you speak louder?
RISC-V is little endian, right? You told in the first one. So should we go from low address to high address? By low you mean like lower number of register, right? Like X5 is a low address.
Yeah. So that's in memory. This is in the stack.
Okay.
Yeah. Questions?
Yes. Yeah, so the negative 34. So when you say like it's starting, the negative 24 is the highest address. So when you're going from to lowest address, can you use like negative 16, negative 8 and stuff like that as well?
Yeah, but since we are pushing three items, 3 registers, X5, X6, and X20, we have to go 3 double word of 8.
Oh, so you have to first count how many you're pushing and stacking. And
Yeah. If you were pushing 1, we would have need only just one 8.
So in this case, the SD and LD, the order matters, right?
Yes.
So if you flip any of them, what will happen?
I mean, in this case, since we are only adding and deduct,
Yeah.
But if it was a multiplication or division, yeah.
Right. So let's say you have 7 S5 at 16 and X6 at 8. So 16, 8, 0. So when you're loading and taking out, there has to be 0, 8, 16. Right? Then can we do it like save 0 and then 6, 8 and 16? Can we do that? Can you flip the numbers too small from large? Will it make a difference?
Because the way the addressing works in a stack in computers is starting from the high address.
Okay.
Because you want to make sure you have the access to the last item you pushed in. You want to pop that first. Okay.
So in the instruction OPF to return register, why we chose X10?
Which line?
The ADDI X10, X20, 0. So I mean there are 4 registers, right? X10, X11, X12, and X1. So why it only shows X10?
I'm sorry, I'm lost.
So copy F to return register that instruction.
To return to register, which here?
No,
Here?
yeah, this one.
Okay.
So why we chose X10?
Because that was the register that contains the return register. In this case, yeah, we should have used that one. In that case.
How do we know X10 is the right one?
Because there are a set of registers that you need to use for certain operations, right? So I was perhaps showing it somewhere here. So 10 to 17 was for that. I'll give you the full register combinations. I guess 2 sessions ago we had the discussion about it. Let me just find it out again if I have it here, so you can have them all. Yeah, here. You see? This is the combination for RISC-V. So from X10 to X17, you can only use that for your argument or results, right? And some of them are preserved and some of them are not. We'll talk about it today. So you start from the 10. Perhaps for other functions you could have needed the 11th one and the 12th one, right? You got the idea?
So can we choose X11?
Yeah.
Yeah. Okay. Yeah. Okay.
Yeah.
So X12 as well, right?
Yeah.
Okay. But not X1.
No, X1 is so every.
Okay.
You guys always want more. Like
I mean,
you have.
convention will be on the switch bar, right?
There is what?
This convention choose register will be on the.
Yeah, this convention is chosen by RISC-V Foundation when they were designing the ISA, right? So X0 is always your 0 constant. And that's why you can only use that X0.
Okay.
Right? Each of those, if you take a look at your green card sheets, they're all there. Yeah, I'm seeing one green card over there. Yeah. Yeah, go.
Okay, so for the stack, if we had more registers that we're saving on the stack, would it be minus 32?
That's right.
And okay, I have another question. You know that add line where it's X6, X12, X1? Why is it X1 and like not X13?
Which line?
The add one above the subtract. Because it said that it stored the parameters in X10 to X13, like in the slide before.
Right.
So like, should that be X13 instead of X1?
Is it X1 the collie?
Yeah.
Yeah, yeah.
So that
Why
would
is
be
it
a
X1?
mistake.
No, X1 is a color.
But shouldn't that be X13? Because you're adding the parameters. Like go to the previous slide. It tells you that it says G2.
Oh yeah, perhaps that's, yeah. Let me double check it. Yeah. Good catch. Let me just double check it. Let me see. That's right. It's 13. Yeah. Good catch. All right, so I'll make sure I'll update the web the slides for you. So that's 13. Thanks for pointing that out. Yeah.
So you just said that because X0 when the value is 0, right?
X0 is one of those 32 registers that only works with 0 constant. So if we want to add addi something, you're gonna addi that with X0 towards your destination.
Oh, So
Yeah.
the value in x0 is not 0.
Yeah, it is 0. It is 0. So so say you wanna store value 10, right? The way you do it is like you add 10 to that x0 towards your stored register.
But at the end, the value of x0 is not 0 because we are adding something else.
No, you're adding it to the 20. You're 0 adding 22, 20, saving it in x10. So you didn't change the 0. 0 is just like a number 0.
No, I mean x0.
X0 is 0. X0 is just.
Like,
X0
like the last line.
It doesn't change.
Could you explain the last line?
Yeah.
So JALR here. Guys, this can be your question as well. So just pay attention here. So JALR is gonna we call it procedure return, right? We're gonna jump and link register. So just like JAL that calls that, we want to return to that call, but jumps to 0 plus the address in x1, right? So now that operation JAR in this case is going to use x0 as registered destination, right? And x0 cannot be changed. So that's the convention for JAR. Got it?
Can you explain again what do you mean by use x not as destination you said?
So x0 would be the destination for the register that contains this address to jump back to your call later, right?
But that should be in x1, right? That address is already in x1.
X1 contains the value, but you have to check the memory address for that. 0 of x1.
Yeah.
Yeah.
And what about that x0 register? What is the use of that?
So in other things like addi, you would have used it as a 0 constant, right? A register for 0 constant. Here, it's going to use x0 as your registered destination, which cannot be changed. You'll see another example. You'll figure it. Okay, but make sure to ask it again so I don't forget. You had a question?
That was it.
Okay. All right. So now we understood. That's a list procedure. Yeah. So when we want to so when we want to do when we want to execute a procedure in a stack, right? We want to make sure we won't lose the value of the what we are executing in that stack for later uses. It's just like inside your function, your scope is within that function, right? But still within that function, you should be able to access those variables, right? So say you start my function A, and then inside that you're gonna calculate and I don't know, compute some other variables. Inside that, you need to be able to have some stack in memory with different addresses that you can access those functions. Like you're executing a code, and then you reach your function f, and then inside that function you have like a plus b, c, and then d is like, I don't know, c multiply a, and so on and so forth. So we need to have this available up until we haven't reached the end of the procedure, right? So we are allocating memory here by changing the sp here by 8 times. Every time we need a register for that. At the end of the day, when we are done with those variables, so we don't need them, right? We need to pop them out of the stack because we want to make sure that we use the stack for other things, right? So by every pushing, you have to change the sp by -8, and you add another register. By every popping, you do the reverse. So you add it +8, and it's going to be popped out, right? Yeah. All right. So let's just have another recap the type of register we use here. So x5 up to x7 and x28 up to x31 are going to be the temporary registers. And x8 and x9 and 18 up to 27 will be used for saved registers. Okay. Now that was one of the examples of a leaf procedure. So let's see if that procedure was not leaf. So it was calling something else inside that procedure, right? This can happen many times in your code. So for instance, you have your own code, like I don't know, print my code, and inside that you want to call another function, right? So in that case, that procedure won't be a leaf one, but rather it's going to be a non-leaf procedure. So we call that a non-leaf procedure if it's going to call other procedure when you run that specific procedure, right? It's sort of a nested call. So what we need to do in order to implement this is, first of all, is return address. We want to make sure we return to where we started. Again, we need to have any argument and temporaries needed after the call. And then we need to be able to restore the stack after the call. Okay? So as an example, let's have a look at this C code. So by just looking at it, you'll understand the difference between a leaf or non-leaf procedure. So here, when we run our procedure fact, which is the name fact, that returns a long int, inside that, right, we return, I'm sorry, it should be 1. I'll fix the slides. Let me see what version I'm looking at. Yeah. I had already fixed it, so this is my side. All right, so when we are executing this non-leaf procedure, which is called fact, if we check if n was smaller than 1, we're going to return 1. Else, we're going to return again fact, right? So now we are calling a nested function inside that. So how are we going to implement it in RISC-V now? So as a start, we know that the argument n has been stored in x10, and the final result is in x10 as well, right? So we have a function that takes as input a long int, and it's going to return either 1 or return a factorial of that n. So it's just a factorial function. N multiply what it has been computed in the last iteration. Okay, so now instead of 1, we have 2 here, because we need to make sure the branches are correct. So the first time the fact is called, st saves an address in the program that is called fact. Okay, so right here. I'm pushing 2 in my stack. That's why I have to deduct it by 16. Question up to here?
Yeah, so for every register you need, you just push 8?
Because the addressing is 8 by 8, right? Each double word is 8. Okay. So now up to here, I know that this is the first time I'm calling fact. So st saves an address in the program that is called fact. Okay. So now, after checking here, after checking that n was either smaller than 1 or not, so or bigger than 1, if it was indeed smaller than 1, fact returns 1 by putting 1 into a value register. Okay? Pops the 2 saved values of the stack and branches to the return address. So that's for the case that it was n minus 1. Indeed.
I have a question. If it's a last come first serve, how come you aren't saving the 16 stack point? Because you do 0 and 8, but you don't do 16.
I didn't get your question.
Okay.
Can you rephrase it?
Okay, so you know how in the previous question, you had minus 24,
Right.
and then you started with 16.
I
And
started
then
with
you went
16.
to 8 and then 0. Wait, never mind. Shouldn't display. Wait.
Okay, so while you guys figuring it out, let me just continue. Okay. All right. So in one case, we have to check if n minus 1. Oh, I lost the thought. Okay, so where were we? So we need to check if n is smaller than 1. We're going to return. Otherwise, we're going to continue with the nested loop, right? And that's exactly what these two are doing. So we're going to branch if greater than. So if x1 and x5 was greater than x0, which is the value of that, we're going to branch to L1. This is the case that we are calling it again, right? In this case, we're going to do an addi with our n, because we want to make sure we have the factorial of n minus 1 as well, right? We call fact n minus 1. After that, we do an addi because we want to move result of the fact n minus 1 to x6. Remember these two loads? They're going to restore colors n and return address. So they have the old addresses we save above, before here on these two stores.
Sorry, that's the problem. There's a problem I want to ask about the load and save. Because you save x1 and x10, right, at the beginning. And then if the BGE code doesn't work, let's say x5 is smaller than 1, smaller than 0. So the BEG doesn't work, so it will continue going, right? It will never go to L1 if the condition fails. Then add sp.sp16. You're not loading the x10 and x1 off. You're only taking the x10 and x1 off at the L1 stage, right? Then
yes.
I mean, how is that even making sense?
Because that function only returns 1. You don't have to do anything. We return 1 and then we step out of the function. If that wasn't the case, we're going to go for return n multiply factorial n minus 1. So in the first case, we just don't have to do anything. If this one wasn't met, we just return minus 1 and it's going to jump out of that. But if the condition was met, we start doing the rest of the thing that we have to do in L1.
I mean, if we ASCII something, so we can load something, right? I mean, we save something in x1, x10. And then
but before that, we didn't know if it's
going to be used.
Yeah, that's right.
Oh.
And then at that point, we've already lost those addresses if they were needed. Could you be louder?
With the jump and link x1 to back, the one right under L1.
Okay.
Yeah, so pretty much we're just saving x1 to the function back.
No, we're just jumping to fact and placing it to x1, and fact was here. So if we arrive up to this point and we thought, oh, we need to carry on more, we're gonna go here, and then we deduct 1 from n, right? And when we go again back to fact. Okay, it's a nested function, just like I'm sure all of you guys know what the factorial function is, right? So you keep calling the previous result. It's a nested function. That's why you want to come back again and again and again. Cool. Here, because after that we need to compute n minus 1 fact as well, because the code needs that, right? You want to use this, right? We need to have both n and n minus 1 here. The fact of n minus 1 and the n. All right. So we reach up to this point, and we're gonna load them back. So we restore the call as n with the old addresses we saved here above. And at the end, we're gonna have the mul, which returns the result of n multiply fact n minus 1. And finally, we're gonna return to the caller. Again, just like the previous example, 0, x1, x0. Okay? So now you saw two examples, one a leaf procedure and the other one a non-leaf procedure. So let's see in general what type of registers are going to preserve and which of them are not. So the ones that are going to be preserved, I'm referring to your figure 211. If you want to have, if you have your book available, you can have a look at it. So those registers that are going to be preserved, yeah.
Sorry, could you explain what this means by preserved?
So yeah, I was just going to say that. So by preserve, I'm talking about the scope of a register when you run a code segment, right? Is it going to be preserved only on that procedure? Is it going to be preserved outside that? Is it a global one or not? So these are different, different tools that RISC-V give you, just like any other, architecture that you can use that. So what's not preserved are the values inside your temporary registers. So somebody was asking me, why do you use that specific register? Because it has that specific functionality. So if you use a register to store, if you use a value to store to a register x5 up to x7 or x28 up to x31, these are temporary registers, right? After you exit that procedure, it's going to be gone. Also the result registers, x10 up to x17, after the condition was met and you're outside the procedure, it's going to get gone. So you don't have the access to that value anymore. But those that are preserved are either in saved registers, which are only at x8 and x9, 18 to 27. And then your stack pointer, frame pointer, return address, and the stack above the stack pointer. Okay? So let's have another view of the local data on your stack. So just by looking at this on the second example, you figure that sometimes you should need to be able to have another pointer other than your SP, because SP sometimes cannot handle all the cases that you want to handle, right? So we call the other one FP, which is frame pointer, and let's see what that is. So a frame pointer, as you know, stack is also used to store variables that are local to procedure, but do not fit in registers, right? Such as local arrays or structures. Normally RISC-V uses a frame pointer. In the next example, it's going to be in x8. So always x8 in your register contains your frame pointer, that FP, to point to the first double word of the frame pointer. So the reason we use that FP as our x8 register is to point to the first double word of the frame of the procedure. So you just have to note that a stack pointer might change during the procedure because we are just deducting and adding to that, right? And sometimes it's not a good reference to come back to where we were in local memory, depending on the offset we had. And that's one of the major that's one of the main reasons we use a frame pointer, because it offers a base reference when we want to come back after the procedure. Okay, you understand why we use a frame pointer and also SP, right? Yeah. All right, let's just recap what we have seen for RISC-V. So x0 was the constant value, x1 was RA, x2 was SP, and then so on and so forth. You can have a look at it. Some of them are having a functionality to be preserved. We talked about it before. Some of them are not. Okay? Let's also recap what a memory layout is. So your memory can be used in different, sort of layout or segments. So one is reserved normally, no matter what you use, as long as your OS is running, your operating system is working. Some of that is reserved for your OS, right? Some other layout, some other segment of your memory is going to be used for your text programs, any other program you are using, right? You have some part that I mentioned, the stack, which is the automatic storage, and they are local to your function. That's why you use SP for that. And you have another, side in memory, which is a dynamic data. We call it sometimes heap. In C, you can access that by the method malloc or memory allocation, right? Sometimes in other languages you can use new for that, depending on the high-level language. And we have another side that is static data. Okay. Now, when you write codes from now on, depending on different functionality that you are writing, you know that different segments of memory is getting used to store that, right? So we have dynamic data or heap, we have a stack, we have some part that is reserved for your OS, we have your text, and we have also a static data. Okay, this is just an example of that memory layout. So your SP was pointing in your local stack, right, with that address. There is another one called program counter that is reserved. It's going to point to the program that is going to be executed in your OS. For your dynamic data or heap, so I mentioned that we're going to use malloc or new in Java. So when you use news in Java, the variable that was issued is going to use the dynamic data or your heap to save, right? In C, we're going to use memory allocation. All right. So let's just have a quick shift of other, functionalities that your RISC-V enables you to do that. What if, so nowadays, representing characters are very important. Your chatting applications or many other applications are visual, most of them, they need to be able to show and process in certain ways some characters, right? So how are we going to present those characters in memory? Do we have a convention for that? And how do we address those, right? So and a standard came out, which is known as ASCII, right? Stands for American Standard Code for Information Exchange. And it has defined 128 characters that are referring to your characters that you want to use, like A, B, C, D, up to your Z, and other characters. So each of those are having a byte encoded character set, right? Some other languages might have different conventions, such as Java has a Unicode, which is a 32-bit character set. So if you have a look at it, this is the ASCII table. So you can find each of those characters that you're interested. For instance, A, right, has its own ASCII value, @ underscore, left parenthesis, right parenthesis, and so on and so forth, right? So it is representing the ASCII value that is encoded in bytes. So if you want to use it, you need to pass the value in bytes. Now let's see how we're going to do that in the ASCII of RISC-V. Okay. So there are a bunch of other operations that you can use to load and to store bytes, either half word or word in RISC-V. So LD, so load and store would be sufficient for transferring byte as well as word, right? We could have only used load and store. However, because of the popularity of text, those founders, they needed to come up with some specialized operations that do that by byte, which is going to be more optimized. So in this case, RISC-V, provides instructions to move bytes. So if you want to, transfer some text, we need to just find the corresponding bytes for that, and then we move the bytes by bytes. Like hello is going to be the H, E, L, L, and O. So we have to find the ASCII equivalent of that in bytes, and then we use these operations to move them and offset them bytes by bytes. Right? So now we're going to have a different issue here. Can someone tell me what's going to be the issue by moving byte by byte? I mean, no. So text, as you know, they have a variable length, right? So now we have to come up with a convention. How are we going to understand when and where my text is starting and when and where it's going to get, ended, right? So in general, we could have come up with 3 methods, right? Java uses one, RISC-V uses another one. So for instance, Java uses the first position, and the first position is reserved to give the length of a string, right? So Java uses this convention. It's going to use the first one as a base. Another method could have been to just accompany a variable length to the string, which was pretty cumbersome to implement. The other convention that RISC-V is using is, instead of starting the first one as a base, why not find a way to have a null character at the end of each of those texts, so that when we hit that, we make sure that the text is over. Okay, and in ASCII there is one that is called null. I'm trying to find that. Yeah, it's just too much. I can't find it here. So in ASCII, it is called a null, right? And it's going to mark the end of the string. And that's what we're going to use here. Okay? So we can parse the code. When we hit that null, we're going to understand that that was the end of the bytes corresponding to that text. Question?
Yeah, sorry. These commands, are you just trying to use them to load words into this?
Yes, load and store. Yeah. Yeah. So for instance, so this C code, this high-level language C code, so we're gonna str copy in C copies the strings, right? I'm sure in Java there's another thing, in MATLAB, in Python. So in C we use this str copy, the first character, the second one, and the size T of I, right? So this str copy copies the string Y to a string X using the null byte termination, right? And it's going to terminate when it reaches the null byte. So the way we can implement it in C is we start from I0 while x of I is equal to y of I. I mean, while this condition is not hitting the null character, which was like 0, we're going to continue. Okay? So now let's see how we're going to implement this in RISC-V. All right. So that's my str copy. I have one L1 and one L2 that corresponds to my ADR of y of I, and then restore the save x19. So at the start, I'm going to assume base addresses for x and y are found in x10 and x11. So x10 and x11 here so x10 and x11 are assumed as my base addresses, right? Note that we don't normally, we don't have to multiply by 8, since y is an array of bytes here. Another double word as prior examples. So when we check here, if I is equal to 0, then exit, that's actually checking for the termination of the null character at the end. Okay? Does that make sense here? I'll pause for a while so you can have a look. So again, we are pushing 1 to x19. We have to deduct. You have to adjust that stack for one double word. Each double word is 8 in address, so it's -8. So your SP goes down to here, right? You initialize your I as 0, and you start your L1, right? You start your y of I as the address. So you store that to x0, the first address of y of I, which was stored in x5, and then at x7 you're gonna ADR of the address. So the address of xi would be stored there. Then it's gonna match these two. So x of I becomes will be equal to y of I. Then we check the termination. If we hit the null character, we need to exit. Otherwise, we need to exit up to x2. Otherwise, we continue. Otherwise, we continue here to addi. Addi just adds 1 up to I. So we're gonna go for the next character, and then the next iteration of loop starts with another jump to L1, right? So it's gonna go back here. Is it clear?
Just a quick question. What's X10 then? What's that standing for?
We assume the address for
Y.
yeah.
X10.
Yeah. Okay. At the end, we're gonna just jump back to the color with the same method x0, 0, and x1. Okay. All right, so I'll wrap up tonight with a few more slides. So let's see how we're gonna do the 32-bit constants. So as you know, most of the constants are small, right? However, 12-bit immediate still is sufficient for that, right? But sometimes for occasional 32-bit constant, what we're gonna do instead? You remember previously we were using LUI and addi for load upper immediate, right? So here for occasional 32-bit constants, so we have to use LUI RD plus the constant, right? What it does is it copies the 20-bit constant to bits 12 to 31, right? The MSBs of that register of interest. Then it's going to extend bit 31 to bits 31 up to 63. So it's going to extend it from one word to double word, right? So that was 32, that was 0, that was 63. So it starts with here, and then it's going to extend it to the full word, right? And then afterward, it's going to clear the bits 0 to 11, makes them 0 here. So that's the way we do that. So as an example, if you want to load this constant, how are we going to do it? 976, right? So what it does is extend it to 64-bit. It's going to copy the 20 bits from 12 to 31, and it's going to then extend it to 64 bits, and then it's going to clear the first 12 bits of that. Then we can do the addi and do the rest of the things to match the number we want to have. Is that clear? Oh.
So after, let's say after addi, you do another LUI, the same register. Then
After addi?
Yeah, so after the addi instruction, you do another LUI to x19. It's going to clear the rightmost 12 bits. Is that what's going to happen?
No, but by doing the LUI RD constant, we're going to do that.
Yeah.
Yeah.
Yeah. So
we've already done that.
After we've done.
Yeah, that's right. Yeah, after that. Yeah.
So after we've done that, we do the addi.
Yeah.
And after we do addi, we do another LUI. If we do another LUI to the same register, it's going to clear the bits from 0 to 11.
Why do we need to do that?
Because I can.
I mean, you can do anything if you want, yeah. But so what's the purpose for that?
I don't know, just curious.
I mean, you can do that.
Yeah, but
Yeah.
it's going to erase it, erase the bits.
Yeah, it's gonna erase it.
Or it will just add on top of that bits.
It's gonna erase it again. So yeah. I mean, why not try it on your RBS and yeah, report the results. You can play around with anything you want. Questions? Yeah.
How does the extended line works?
Can you repeat your question?
How does the extend base 31 to this work?
Oh, extend. Okay, so if you want to load a big constant, right, that doesn't fit in 32 bits, you need to expand it to double word. Double word has 64 bits, right? So you start from 32, the upper 20 most significant bits of that 32, and then you extend it to 64. Is as if you add more zeros for that.
I mean, if I don't use do statement, there will be only 12 bits for me to work, and if I use the lose statement
With addi.
with addi,
Yeah, with addi.
then I have a 64 bits.
Because addi, if you remember in your pre-lab,
Yeah.
last lab, so it's gonna work either from 0 to 4096 as an unsigned, or minus 2048 to the plus side, right? So that's the limitation of addi. If you wanted to load something bigger, we would have used LUI with addi.
The new statement only allowed us to use the bits between 31 to 13. So how can I use the bits from 63 to 32?
If there was a huge constant, it would have been used.
I mean, the new statements have only 7 bits IMM, right? So how can this thing store something more than 7 bits?
And so that's exactly why we use LUI, RD, and constant here. Because it's going to copy the 20 most significant bits from the 12 to 31. And then it's going to extend that to double word. And then it's going to erase the first part. So it's a 3 steps. So 3 steps. I guess you guys are getting tired, so I'm just going to finish it in 2 minutes. All right. So let's just, like 2 more slides. So how are we going to address branches, right? So we have something called branch addressing. So branch instructions specify opcodes, specify 2 registers and a target address, right? So we have 2 registers, a target address, and an opcode. You can find all of those in your green card sheet. So the way it does is we can do like this. The program counter has the relative address, right? So we can only jump up to a certain distance from the program counter. So the SP type in RISC-V in branch instructions, as I mentioned, works from -496 up to the other side, are the multiple of 2's, right? So if you want to branch to a far address, the limitations in RISC-V would be, I can just give you the exact number. So we can only branch within minus or plus 2 to the raise of 10 in RISC-V, or we can only jump minus and plus 2 to the raise of 18 with the jump from the current instructions in RISC-V. So overall, that's your summary of RISC-V addressing. So we have 4 types. Either it's an immediate addressing with its own set of presentation. Either you have a register addressing that you knew already. Either you have a base addressing, right, using your SP. So remember that this base addressing uses memory. And the 4th one that we just saw now is going to use a PC relative addressing, right? And you can refer to this table for all of those presentations. All right, guys. Make sure to ask questions from your TAs on Friday if you had one.